Professor John Kymissis is the Kenneth Brayer Professor of Electrical Engineering at Columbia University. He is a fellow of the Institute of Electrical and Electronics Engineers and National Academy of Inventors. His research focuses on the fabrication, characterization, and applications of thin film electronics. At the Columbia Laboratory for Unconventional Electronics, researchers fabricate devices and systems using low thermal budget techniques for a variety of applications, including sensing, display, and energy conversion. A number of these systems have been advanced to commercial use. But what is thin film electronics? What uses does it have in building a more sustainable world?
Electronics generally are made using materials known as semiconductors. And silicon is by far the most popular semiconductor. And I'm sure you've seen pictures of people holding up wafers and walking around with them, which is not how you usually use them in the factory, but that's a different story. You're not supposed to touch them with your bare hands. But most electronics today are made using single crystal materials. So that silicon wafer is a large, huge single crystal of silicon, which is cut into plates. Those plates are what we call wafers, and then the transistors and other devices that we use are built on top. Thin film electronics is a different technique. Instead of starting with a single crystal, which is perfect, we instead start with a piece of plastic or a piece of glass, and we deposit semiconductors on top, and that's called the thin film process. And so using that approach, we can use a different type of substrate. We're not limited to the not infinitely large and very rigid silicon wafers, and so we can make things that are flexible. We can also make things that are transparent and that are on glass. And so that's the general area that I focus my research in. Now today, about 80% of the market in the world is crystalline electronics, and about 20% is thin film. And most people don't recognize this, but the display, for example, in your TV or in your phone is made using thin film electronics. In your TV, you start with a large piece of glass, and there are millions of transistors on that glass that control the display. And also in your phone, there's usually a piece of plastic, and the electronics are built on that plastic, which is then laminated on top. And the fact it's made from plastic makes the phone lighter, and it also makes the display thinner, which allows more space for the battery and other electronics. Now, in terms of the research areas, my group has been looking beyond displays. So one area we're really excited about is making large microphones. And why would you want to make a big microphone? So sound, when it travels, has a wavelength which ranges from the millimeters to the meters, depending on the frequency. But if we think about like ultrasound range, tens of kilohertz, that's a large enough space that we can actually see it using microphones, but the microphones have to be big enough. And so we have a whole technique of building electronics on piezoelectric materials, which then allows us to make these big microphones. We've used that to make very large microphones that can see sound and measure turbulence. And we've also used it with some other collaborators to make very tiny microphones that can also fit inside the ear. And all of them use the same general idea, but in different applications. Microphone in the ear, so that which we're developing together with the lead there is at Mass Eye and Ear Institute. The goal there is to make a microphone which can work for a cochlear implant user. Normally, if you know anybody with cochlear implant, they have a headset outside, but they have to take that headset off when they take a shower, when they're doing sports. Kids, when they wear a helmet, have to have it off. And so in order to increase the period of the day where the implant works, the idea there is to put the microphone inside the ear. And it turns out that the ear is a great place to pick up sound. I mean, there's been other work on this, like putting microphones under the skin, and it can work, but sometimes it picks up other noises. And so we've been working on measuring what's happening inside the middle ear and the inner ear as an alternative. One of the other areas, and this is something we've been working on, but lots of other folks have been working as well, is in making medical sensors that are the size of the human body. So we've shown that by measuring the blood flow that's in the skin and on the brain in particular, that we can diagnose certain diseases. And in particular, like epilepsy is a great example of this. And we work with a group at Cornell on mapping where epileptic seizures happen in the brain. And today that's mostly done electrically, but our collaborators have shown that if you measure where the blood is flowing, you can then tell where the epileptic seizure focus is. And that's important if you're considering surgery for resolving the epileptic seizures. And so we've shown that we can use thin film electronics to make a large enough sensor that measures using optical techniques and basically measuring the color of the brain. We can see where the blood is flowing, and from there, with a higher resolution, detect where the epileptic seizure is starting. And that can inform the surgery, which then happens afterwards. I'm sure you've seen the videos of opening up the skull, and it takes like a whole day. And that's because, unfortunately, the electrical survey only gives you a resolution of about 1 centimeter. And our technique allows a resolution of about 100 times better, in principle at least, so that you have a better starting point, not moving 1 millimeter at a time. It allows a higher resolution because that blood flow change happens at the 100 micrometer level, not at the centimeter level. Now, in terms of sustainability, there are lots of ideas with thin film electronics. I mean, the most successful, for sure, has been the development of photovoltaics using thin film electronics. There's been a lot of work here in India on this as well. And one of the nice things there is, when you make a photovoltaic cell with silicon, there's actually a lot of input, like energy input, needed to make that cell. And you usually don't cross over for 5 or 6 years after you make the cell in the energy that you put in. So if you want to have like a net zero scenario, silicon photovoltaics, they're not terrible, but they're not amazing either, because you're just paying back the carbon for about 1/4 of the life of the cell. With thin film electronics, on the other hand, organic materials, and more recently, perovskites and certain compound semiconductors, you can have, because you don't have to melt the silicon and purify it, the crossover point can be much sooner, like often less than a year. And so that also allows us to reach a better level of carbon neutrality as one of the application areas. But in the US, the #2 solar producer actually makes thin film cells. And that's because those cells are light enough to be put on the roof of buildings without the need for new hardware. That's actually what people are excited about. Yeah, they're a little cheaper maybe, and that's fine. But the fact that you don't have to put brackets and support all that weight has been very attractive. And so they're basically what they call solar shingles, which can be put on the surface. And that's already a commercially successful product. We had a project in what we call the plant spike. So you know how when you go to the store to buy plants, they have like a little flag in them that tells you what the plant is? So one of my students, she had the idea to make this just a circuit board with that same format, which would tell you the health of the plant. And we had a slogan for it. We said, your plants can't speak, but Plant Spike can. And so it would measure the hydration of the soil, the amount of sunlight, and the temperature, and then report that back over a radio. And it had a battery, and it could last for about 2 years. So we developed that, and one of my colleagues, Trish Culligan, who was at Columbia, but now is the Dean of Engineering at Notre Dame, and we miss her, she's a great collaborator. So she was working on tree pits, and in New York and in many cities, tree pits are where they cut the sidewalk and they plant a tree. And the problem is this is very expensive to do. I mean, you have to, get rid of the concrete, you have to dig the hole, you also have to water the plants. The trees don't get watered as well because there's no soil. Anyway, so a lot of the trees die. And Trish was looking at how to understand this. And she found a couple of things. One is that a lot of the trees were essentially attacked when people let their dogs use the tree as a toilet. So that's one issue. So she developed an intervention, and she did a whole study of what kind of tree fence protects the trees the best. And I know it sounds very simple, but each of these trees is a $10,000+ investment. It's a huge investment. And so the second thing is that a lot of them don't get watered enough, and the third is a lot of them don't have enough drainage. So we showed with the plant spike, you can put this plant spike in and then measure the drainage. You can quantify how good the site is, and if the site is not good, you can either change the schedule for watering, you can amend the soil by changing the soil, or change the tree if the tree dies. Pick a tree that maybe needs less water or that handles more water. And so we did that, and that was pretty fun. And then after that, we did a second version of it, which interfaces also with a dendrometer. And I'd never used one before, but dendrometers are so cool because it's like a belt that you strap on the tree, and it can measure how big the tree is. But it's extremely precise. Like, you can see that the tree, when it wakes up in the morning, has lost all of its water, and it starts collecting water as the roots give water. I mean, it's amazing what you can see. And you can watch the tree and the water coming in and out and the tree growing every single day. And so we were able to show correlating the dendrometer measurements with the plant spike measurements, and using that to then map on our campus the trees that facilities thought were at risk. And we were able to then tell them, this needs to be watered more, maybe next time put a different tree here, things like that. So when you look at the greenery in the city, having more information about the site, the tree that you put in, the soil, and we also made a different sensor that could tell if animals were using the tree pit as a toilet. That was a collaboration with another colleague at Barnard College. She makes this very cool surface chemistry, which can be specific for urea. And so with all that information, you can try to optimize the deployment of those greens and get the most bang for the buck out of your space and your investment. Using my knowledge of piezoelectrics, I can make microphones, I can make energy harvesters, I can make, we made a system of microphones that are implanted inside mice to tell if the mice are talking, all sorts of things. And so that's sort of the way that I organize my research. Now, in terms of the application areas, what do we need? We need, the big problems we have, food production is one huge one. And this is true globally. It doesn't matter where you live, but agriculture is just not sustainable. We have, plant productivity is going down for various reasons. We need better conservation of water, but we also need to mitigate the environmental impact. And so, for example, there's an amazing project that we have a small part of, in which we also use piezoelectrics, by the way, just randomly, looking at the breath emitted from cows. And there's a collaborating group with ours which has developed a seaweed cow feed, which they've shown changes the biology of the cow's gut. And again, I know nothing about this, but I know how to make the sensor that measures the breath. And so you feed this about 10% to the cow feed, and the cow emits much less methane than they would otherwise. And so, again, management of water, we've talked about, this agriculture. And then the other big environmental impacts are the environmental waste. And a lot of that is measuring the atmosphere and finding techniques to measure the amount of ammonia in the air and other environmental impacts. So I think agriculture is one huge area because everybody has to eat, and it takes up all of our land, and it uses a lot of our energy. And I think the second big area is, like I said, next generation healthcare. We have in the hospital all the cool tools. You want to know anything about yourself, you can go to a national center, capital city kind of hospital and get answers. But most of the world doesn't live right next to, a tier 1, capital city. How do we take that same information and get it out to, maybe the consumer, but at least the clinic and those other layers? And I'm very excited about the things we can do to look there. So for example, and we haven't started working on this yet, but we're organizing a new center at Columbia in maternal health. And one of the questions is, how do you tell when a woman is in labor? My answer, I want to use piezoelectrics. You can make a band and measure quantitatively no more sitting there with the stopwatch, arguing with the father, whatever, no more guessing, start knowing. And so you can imagine using a lot of those same techniques to get those insights and improve health and wellness. And I'm very excited to see both of those develop.